Hello, my name is Rohan, and I'll be presenting the paper Rule-Based Electronic Phenotyping Algorithm for Detecting Clinically Relevant Cardiovascular Disease Cases. Now, this is my presentation for the 591 TXT seminar for spring 2018. So, the paper that I read tries to address the problem of quality in electronic medical records. Electronic medical records help in error and data loss reduction, patient care efficiency increase, decision making, assistance, and facilitation of event surveillance. They also show a lot of promise in terms of data collection to facilitate observational epidemiological studies, and their use for this purpose has increased significantly over the recent years. However, even though the quantity and availability of the data are clearly improved thanks to electronic medical records, the problem of the quality of the data always remains. And the reason why the quality is such an important trait in EMRs is because if the quality is not good, we might actually prescribe an a diagnosis to the patient which is actually not correct, which might be life threatening in certain situations. The objective of the paper is threefold. First of all, it tends to say that there's a lot of heterogeneity in medical practice because of language barriers, uh, which often result in local adaptations to detection algorithms for diseases to improve their classification accuracy. So they locally developed and validated an algorithm for the detection of clinically relevant cardiovascular diseases based on diagnostic codes from the EMR at HIBA, which is the facility, in a clinical setting. And they then assess the sensitivity, specificity, and agreement levels of a rule-based algorithm for the detection of cardiovascular and cerebrovascular disease using structural data from the electronic medical records. We have to lay emphasis on the fact that the testing of the algorithm was done only using the electronic medical records of one hospital. As a result, um, the accuracy that they got can only be generalized to one hospital itself and to those one particular set of records. So, how was the algorithm developed, which they used? The algorithm development process was basically they hired three family physicians from the research groups. The research groups are mentioned in the parentheses, and they selected clinically relevant cardiovascular disease and cerebrovascular disease terms from the International Classification of Primary Care, second edition, the ICD-10 version, and SNOMED CD 2015 edition. These are all research journals. They then ran a query um, in the HIBA's EMR database. The HIBA is basically the hospital in which they tested this algorithm, which yielded a list of codes that was revised and agreed upon by the three reviewers. So they later on went and did manual inspection just to make sure that there were no errors in the data set. Um, and the terms which were not related to cardiovascular diseases or cerebrovascular symptoms, uh, signs, diagnoses, or procedures were excluded just to improve the accuracy of the classification algorithm. And then terms describing incidental findings without clinical relevance were also included. Um, so, how was the algorithm applied and what was the data set? What was the sample space? This slide basically addresses that. So, the algorithm yielded a positive result if the patient had at least one of the selected terms in their medical records, as long as it was not recorded as an error. And the way that recorded it as an error was basically doing a manual inspection of the records. Else, if no terms were found, the patient was classified as negative. They ran a query in the HIBA's EMR database. This yielded a list of codes that was revised and agreed upon by the three reviewers, just to make sure that there were no mistakes done by a single reviewer. So they had a three point source of failure. Uh, the algorithm was applied to a randomly selected sample of the active patients within the hospital's HMO, and then they later on classified the patients into four groups to actually account for false positives, false negatives, and the actual accuracy of the algorithm. So the four groups were negative patients, patients with cardiovascular diseases but without cerebrovascular diseases, patients with cerebrovascular diseases but without the cardiovascular disease, and patients with both diseases. As we'll see later on, this helped us actually analyze the algorithm a little bit better. So later on, they also did the manual review of the medical records because the data set might not have been actually correct. And the procedure for that was basically the three family physicians participated in this process. One third of the patients were assigned randomly to each reviewer. Both coded and uncoded sections of the EMR reviewed. What this basically means is that every disease had some assigned codes to it, and so some disease there were some diagnoses which didn't have any codes, so they were both reviewed. So the electronic medical records of both those types of diseases were reviewed. So what was the classification for the what was the manual classification criteria? Um, a case was considered as positive if positive mentions regarding cardiovascular disease or cerebrovascular disease, medical history, signs, symptoms, procedures, or some treatments were found in the records, and vice versa. If there was no there was no mention of any clinical notes of the cardiovascular disease or cerebrovascular disease, um, it was dismissed. But also, there was also another reason why they could dismiss a case was because of the fact that a diagnostic code related to CAVD or CEVD was probably recorded, but there was no record of it in the free text of the clinical note. And then there were some unclear cases, of course, and they were decided upon by discussion between the three reviewers. So usually the yielded value was around 0.91 in those cases when there were unclear cases. So let's get on to the quantitative analysis of the algorithm and the results that we achieved from it. The operational characteristics of the algorithm were calculated using the manual review of the EMR as we referenced the test. Each result of the deduction algorithm was classified as true positive, false positive, true negative, or false negative, both for cardiovascular and cerebrovascular pathology separately as well. And then there's also a qualitative analysis, which is more important than quantitative analysis because we have to actually worry about the quality of the EMR records rather than the quantity of the EMR records that we have. So the qualitatively analyzed false positives and false negatives. The reviewers describe the reasons that led them to classify each case as an error. As you remember that the three reviewers actually discussed it amongst themselves if there was an error. So they actually had to give a reason for that. These errors were then grouped together and quantified in different subcategories as well, thus making the review much more comprehensive. This is the flowchart. The sample, as you can see over the sample that we can see over here, potentially eligible patients were 9 n is equal to 1137. So 31 did not fulfill the criteria, as they had been they were just being diagnosed for less than 1 year in the hospital. And then we had 1106 patients which were eligible. And then we ran the algorithm on that, and we got a positive result on 764 patients, and then negative result on 342 patients. Then we did a manual review of the review reference test, and as you can see that the manual review actually yielded a really great result, because of 764 which were diagnosed as positive by the algorithm, now 758 were actually true positives, and n is equal to 6 where there were only 6 cases of the algorithm predicted it wrongly in case of positive results. But in case of negative results, we see that there are 48 counts of the diagnosis being positive, but the negative still outnumber the negative. The negative true negative far outnumber the false positives, false negatives. Sorry, in this case being like 294, which is a pretty good accuracy rate, with more than 80% accuracy. Let's look at the qualitative analysis of these results now. So as you can see that the qualitative analysis of the errors provides information about the physician's EMR usage habits as well, because if the physicians used EMRs in a correct way and they actually record and store it in a proper way and update it, the quality of the EMRs actually improves over time. The high sensitivity of the algorithm is probably due to the relevance of the selected problems, which is, of course, that we are only focusing on two diseases, cardiovascular and cerebrovascular diseases. And if we actually had to lower the lower the sensitivity, we'd have to account for many more diseases, but it would be a time-consuming process, and it would be really hard to actually classify the disease that actually judge the accuracy of the classification algorithm in those cases. The lower specificity found required an analysis of the false positives. The most common type of error was the dismissal of a diagnostic code by the physicians themselves. Was usually related to not deleting or registering the code as an error. As you can see, the third point actually means that it meant a degradation in the quality of the electronic medical records, which is what we're trying to actually improve in this paper. The second most frequent case of false positives are codes that do not translate to clinically relevant events. This basically means that suppose there's a patient with a disease which has been assigned a code, but that disease is actually not clinically relevant in this case, as that has never been encountered before in the hospital. So that the fourth point is actually relevant to that point. Now, as you can see, the qualitative analysis in this case in the results, as you can see that false negatives in this case, which were codes not included in the algorithm, where the total number of false positive and false negatives were 98 total. 20 of them were basically because of the codes was not included in the algorithm, and then 20 of them was basically from n is equal to 32. 20 of them were also because of the code was not included in the algorithm, and then 15 for cardiovascular, and then 5. As you can see that the sum of 15 plus 5 equals to comes up to be 20, which we are looking for in this case. And then there are also some errors because of erroneous data as well. Now let's look at the false positive rates. So dismissed diagnoses, there was a total number of 43, and total false positives in this case was 43 again, because these two numbers have to match. And as we look at it, the ratio of false positives in cardiovascular disease is actually more than cerebrovascular diseases. And then this was the last point in the previous slide, where the coded terms were without correlation and the clinical notes. So as you can see over here, again, cardiovascular diseases far outnumber this, are almost equivalent to cerebrovascular diseases in this case. So as we look over here, this actually is a distribution of erroneous outcomes classified by type of clinical problem. So rather than it being classified as a cardiovascular disease or cerebrovascular disease, we see that how these were the diagnoses that were given by the algorithm, and they were actually wrong. So there was the total number of errors in this case was 98, and the most common failures in this case was cerebral vascular disease, heart failure, acute myocardial infarction, cardiovascular symptoms, stroke or cerebrovascular disease, or transient ischemic attack. As you can see that all of these are actually generally in the category of cardiovascular diseases or cerebrovascular diseases, which is kind of expected because the algorithm basically runs on basically tries to detect those. Let's talk about the summary of so to summarize, the paper basically developed a simple algorithm using only standardized and non-standardized coded terms within an electronic medical record that can properly detect clinically relevant cases of cardiovascular and cerebrovascular disease with excellent sensitivity. The specificity level, as we talked about, is difficult to improve without altering the excellent sensitivity attained, since much of the deficit of specificity is due how users interact with EMR. Perhaps combining it with an analysis of this is a suggestion that if we perhaps combine it with an analysis of the free text using an NLP approach, it might yield to better results. What I thought of the paper, so I thought one of the limitations of the study is that by not limiting the algorithm to standardized codes, it might be too specific for the hospital that we are for the hospital considered in the experiment, not extensible enough, as in like if we had to take this algorithm and actually try it on the EMRs of any other hospital, it might lead to poor accuracy and poor classification. It's also important to emphasize that this algorithm sought to emulate the medical criteria for the detection of cases and not the detection of true cases, since no objective criteria were used in the algorithm or the manual review process. Basically means that we didn't actually try to, we just wanted to see if the case that we're handling is actually, if the patient that we are actually handling is a case patient or not. We're not actually trying to detect if it's a true disease itself. We already have the results from the manual review, and then we actually just try to see the classification of the algorithm that we are trying to test. Thank you.